So, welcome back. So, what did we learn in the last class? We learned about the forward bias and reverse bias PN junction. What is the basic definition? How the depletion width and the built-in potential change with a bias, and we started to understand in details about forward bias PN junction. I told you that when you apply a forward bias, electrons from the N side and holes from the P side are now injected to the opposite sides, and so the barrier reduces, the depletion width also shrinks, and because they are injected, so holes are injected to the N side, they become minority, they decay. So, that decay has a profile. Similarly, electrons are injected from N side to P side, they will decay in the P side, that decay will again have a profile. This profile is exponential decay if it is a long diode, that is what we are considering here, and because the carriers are decaying, the derivative also will be exponentially decaying. So, the current which is the derivative, the diffusion current of holes and electrons in the respective sides will also decay. That is what we had learned. We had established the mathematical expressions for those decay, okay, and we also told you how the carrier profile decays. And now I asked you a question when we ended the class. The total current in the diode or the device has to be same, has to be constant throughout. So, the diffusion currents are decaying, there is something else that is compensating such that the total current is constant. So, that is what we will start from today. Okay. So, we will come to the whiteboard, we will look at the last slide that we had discussed. So, the hole current and the electron diffusion current will decay on the other side. If you recall the, so I will talk about say only the N side, how the holes are decaying, because the same thing can be applied to the P side. So, I told you that excess holes on the this side will decay as P n naught, which is Ni square by Nd, into exponential of q V A by k T minus 1, that is the applied voltage Va, Va is the applied voltage, into exponential of minus x minus W n by L P, the holes will diffuse. Okay. And if I take a derivative of this now, q dP delta P x by dx, this will give you the hole current, the diffusion current because of hole is a function of x. I do not want to, I mean you can do the mathematics, but of course I want to find out this particular value at x equal to Wn, which means what is the diffusion current at this point, at x equal to Wn, at this point, what is the diffusion current here? It will decay of course, but I want to know the diffusion current at this point, at the edge. This is the edge of the depletion region, this is the edge of the depletion region. So, at the edge of the depletion region, what is the value? So, if you take a derivative of this, multiply by q dP and you put x equal to Wn, then you will get this value, and that value turns out to be q dP by Lp into Pn naught, which is the minority carrier hole concentration, which is the baseline, into what? E to the power q Va, that is the applied voltage Va, by kT minus 1. There is no dependent on x because x equal to Wn at this point, right. So, I will again plot it here. So, this is your x, this is your x, okay. So, this is your 0, this is your Wn, this is a minus Wp, okay. So, what is happening is that your whole current is now diffusing like that, right. This is your Jpx, whole diffusion current, and this value I told you is q dP by Lp Pn naught e to the power q Va, the applied voltage, by kT minus 1, okay, that is the value. Okay. Similarly, on the N side also your electrons will decay. At this point, you know, this is electrons is on the P side, sorry, on the P side electrons are diffusing. So, that diffusion current also is dependent on x. At this point, the value of the diffusion current because of electron at minus Wp, that point, this value is given by same thing here almost q dN by Ln, because electrons are diffusing this side, into Np naught, which is the baseline, the background electron concentration is a minority, into e to the power q Va by kT minus 1, the same thing, okay, only this part changes, okay, the exponential part remains the same. Now, these are diffusion components of current on either side. Now, if you recall a PN junction band diagram, if you recall a PN junction, I am just trying to draw an equilibrium, but it is fine, you can draw a non-equilibrium also. You see now electrons are being injected from n side to p side and holes are being injected from p side to n side, and they are decaying of course on the respective sides there. I mean their holes are decaying here, electrons are decaying here. So, you are getting the diffusion current, but this region which is supposed to be a neutral region is not strictly neutral, because there will be some field that will, some voltage that will drop, there will be a very small field that will exist here, and that is why these are called quasi neutral region. So, it is not exactly neutral, and there is a very small field that exists there. Okay, there is a very small field compared to this slope, that slope is almost negligible. So, we write it flat, but there is a small field that is here, very small field, okay, and it is called quasi neutral because some voltage is dropping here. So, because there is a small field here, there will be a drift current also. Now, drift can be because of both electrons and holes, this is n type. So, there will be q mobility of electron times n times the small field plus q mobility of holes times the holes here into the small field. Now, the holes are minority, they are decaying here, the hole concentration is very small, multiplied by a very small field is almost negligible. So, minority carrier drift here or the holes drifting here is very negligible, but majority carrier n is large. So, even if the field is small, a very large n majority carrier will make sure that the drift current because of electron in this region is not negligible. Similarly, the drift current of holes in this region is not negligible, okay, drift current is not negligible. So, those drift current components, and there could be other components also, like majority might also diffuse in small quantity, right. So, all those components will basically make sure that the total current here is constant. So, the total current here has to be constant. I will tell it J because it is the current density, I am not taking the area, J total. The total current is constant, but the whole diffusion current on the n side is going decreasing like this, the electron diffusion current on the p side is going like this. So, the respective drift current will be such that, will be how? The respective drift current will be something like that, okay. Let me use a different color maybe. The respective hole current, the drift current, this is the drift current of majority electron and this is the drift current of majority holes here, drift of majority holes. I told you there is a small field in the neutral quasi neutral region, this is drift of majority electrons on the quasi neutral region. So, the addition of this plus this plus this will make sure that the total current is constant. And I told you that within this depletion region, this is the depletion region, no, within the depletion region there will be no recombination of current, whatever current is at this point will continue throughout here and whatever current is at this point will also continue there, okay. So, let us look at that point again. So, this is the whole diffusion current, this is the value here, whatever milliamp, microamp, whatever, this will not change in the depletion region, okay, this will not change in the depletion region, okay, this will not change in the depletion region. So, it will remain constant, and actually your majority hole drift will start from here like that. So, the total is constant, okay. Similarly, the electron diffusion current that is happening here, this value will not change in the depletion region because in depletion region there is no recombination, that is the idea. So, it will stay flat. Why is it staying flat? It is staying flat because in depletion region there is no recombination. So, it is staying flat, okay. And so, this current will actually increase from here, this is increasing from here, it will increase from here, okay. So, the addition of this current and this current will basically give you the total as a fixed current. Remember, this current is drift of majority electron and this is diffusion of minority holes, okay. So, if you look carefully, the sum of this and the sum of this is actually the sum of any point here, any point is the total current, right. So, this plus this is actually the total current, and you know this value is nothing but this value which is this, and this value is the same as this value everywhere is this. So, can I say that the total current now J total is nothing but the current here plus the current here, which means the current this plus the current this is the total current. So, what is this current? This is this. What is this current? This is this. So, can I add those as the total current? The total current is Q dP by LP, that is holes diffusing on the n side, Pn naught e to the power QVA by KT minus 1 plus this is electron diffusing on the p side, electron diffusing, diffusion coefficient of electron, diffusion length of electron, minority electron based on the other side, e to the power QVBA by KT minus 1. I can write it as Q dP LP Pn naught plus Q dN by Ln Np naught into e to the power QVA by KT minus 1 is given by the total diode current, which is independent of x. Of course, current cannot depend on x, it has to be constant everywhere, the total current has to be constant. So, this does not depend on x, but it depends on the voltage exponentially, depends on applied voltage VA exponentially. You see this quantity exponentially. This prefactor, which is not dependent on x or which is not dependent on voltage, it only depends on parameters like diffusion coefficient, diffusion length, diffusion coefficient, diffusion length, which are material parameter, and the minority carrier concentration. This prefactor can be labeled as Js or J naught. Some textbooks call it J naught, some people call it J naught, Js. It's actually called reverse saturation current. Okay, I'll come to why is it called like that later on. It's called reverse saturation current. Okay, and this value is typically pretty small, like picoamps or femtoamps, this value, but this is multiplied by large quantity. Okay, because this quantity becomes very large as V is increased. So, I can write the total current J total is equal to J naught times e to the power QVA by KT minus 1. This quantity becomes very large soon, so one can also be neglected in forward bias. So, what I am trying to say is that if I plot J total versus VA applied voltage, look at the formula, J total is equal to J naught e to the power QVA by KT minus 1. If your VA is 0, then e to the power 0 is 1, 1 minus 1 is 0, so it will be 0. So, at 0 volt there is no current, makes sense. Now, as you slowly increase VA, it will slowly increase, okay, but in linear scale, if this is linearly, you are plotting the linear scale, which means 10, 20, 30, 40 and so on, then initially it will not show you anything, it will basically, it is yet to turn on, there is something called turn on. At some point it will turn on and then you will see an exponential change. Actually, this is already increasing here, but you cannot see it in the linear scale, you have to see it in a log scale. For example, at this point, say this point may the current might increase from picoamp to nanoamp, but if this scale is milliamp, 1 milli, 2 milli, 3 milli, 4 amp, then you cannot see a change from microamp to nanoamp or nanoamp to microamp, right. That is why it looks like that. Okay. At one point it will turn on, it is called the turn on voltage, and it will increase exponentially. It will increase very exponentially. This is your turn on voltage, and the turn on voltage is almost equal to the built in voltage. It depends on the built in voltage and hence the band gap. If your band gap of the semiconductor is large, the turn on voltage also will be large, by the way. Okay. So, for example, if this value I told you is very low, suppose I take a value of, say, this is current density. So, suppose this is, even if you take absolute current, which is I, it will be I naught. So, suppose the absolute current is, say, 1 femtoamp, 1 femtoamp is 10 to the minus 15 amp, and this VA, if applied voltage is suppose 0.6 volt, then e to the power 0.6 divided by KT is 0.026, minus 1 can be neglected, it is very small. This is equal to e to the power how much? Maybe 22, and e to the power 22 is a very large number. See, e square is almost 10, it is not exactly 10, but close to 10 you can say. Okay. So, e to the power 22 will be equal to 10 to the power 11, almost slightly more than that, okay, or slightly less than that. So, you can say that total current at 0.6 volt is equal to 1 femtoamp, which is 10 to the minus 15 amp, times 10 to the power 11, which is equal to 10 to the power minus 4 amp, that is equal to 100 microamp. So, see, from 1 femtoamp to 100 microamp or 0.1 milliamp, this is the same as 0.1 milliamp. See, from 1 femtoamp to 0.1 milliamp, the current increased from this to that. It is a huge change in current. So, it can increase exponentially, okay? It can increase exponentially in the forward bias, right. So, a small change in the applied voltage will lead to a very large change in the current, okay. So, that is the beauty of forward bias. There are many things that we will keep referring to when we are discussing PN junction. I will also refer to how LEDs will work, how detectors will work and so on, solar cells and so on with respect to PN junction equations, okay. I will come to that in subsequent classes. So, now what again you have to think about here is that suppose J is equal to total current J naught. What if the applied voltage is negative, say minus 1 volt or say minus 2 volt or say minus 0.3 volt, whatever, what will happen then? So, you see this term e to the power q V A by k T minus 1, right. If your V A is negative, then this quantity becomes very small. Very soon this quantity will become almost 0, right. So, for example, V A is minus 1 volt. How much will that be? E to the power minus 1 divided by 0.026 minus 1 into J naught. This is equal to J naught. E to the power minus, this will be like minus 20, I do not know, this will be like minus 25, no, more than that. So, 1000 divided by 26 is like minus 40, e to the power minus 40 minus 1. What is e to the power minus 40? Almost 0, it is 0 almost, right. It is 10 to the power minus like 20 or whatever, right. So, this is 0. So, 0 minus 1 is minus, so this will be minus J naught, which means at reverse bias voltage your current saturation current is the total current in the diode is actually minus J naught, which is reverse bias current. Of course, if your VA is very small negative, say minus 0. At very small, like minus even minus 3 volt if you talk about, that will be e to the power minus 0.3 by 0.026, that is like minus 1, that is like e to the power minus 10 minus 1, which is 0 almost. So, essentially in reverse bias J total is almost equal to minus J naught, because this term becomes very small, almost 0. So, in reverse bias essentially, so if I plot this on the reverse, this is on the forward bias side, it increases, right. On the reverse bias side the current is actually very small like this, and that current is given by, it is very small current, that current is given by minus J naught, it is the reverse bias saturation current. So, on the reverse side say minus 5 volt, this is minus 4, minus 3, minus 2 and all so on. So, the current is very small. On the forward side after a turn on it will increase a lot. This is called rectifying behavior. The PN junction diode can behave as a rectifier, because in one direction it can lead to a large current, in the opposite direction it will lead to a negligibly small current. That is called rectification, which when a diode or a device allows current to flow in one direction, but does not allow current to flow in another direction, is called rectification. So, a PN junction diode can behave as a rectifier, and this is what is very obvious from this expression and the mathematical analysis. At very large voltage the diode will break down like this. We will come to the breakdown little in one of the next classes sometime, okay, maybe next to next class or so. Diode will break down eventually at high voltage, that is a different phenomena, but until that point your current is very low, it is given by minus J naught like picoamp or femtoamp. On the other side this current can be very large like milliamp or amp. So, essentially you are able to rectify this, that is why PN junction diode is called a rectifier, it can work as a rectifier. Now, I told you that if I plot a negative voltage here, this quantity becomes almost this, but physically what happens? Can you also look at reverse bias junction physically? Can you look at reverse bias junction physically? That is the question, okay. So, look at that now. So, I will draw a reverse bias junction. A reverse bias junction, the depletion becomes larger, okay. So, this built in voltage has become large by QVBI plus VR, it is a large, it has increased now because this is p type connected to negative, this is n type connected to positive. Carriers are being drawn away, so the depletion region has also become large. In reverse bias, what is happening is that holes are not injected in this side, right, they are actually taken away. So, this edge, this is a edge, right, edge of the depletion region, this is an edge of the depletion region, this is also edge of depletion region. At the edge of the depletion region, we assume that free carriers, that is electrons and holes cannot exist at depletion edge. The reason we assume that is that we assume that at this depletion edge there cannot be any mobile electrons or holes, okay, at this edge. Okay. I mean when I say electrons or holes, I mean minorities specifically, okay, because the moment there is a carrier, it will be swept away by the field. You see this field is huge, this is a huge slope. So, in p side, what is minority? Minority is electron. So, if the electron happens to come here at this edge, it will be immediately swept away to the other side. And on the n side, what is minority? Hole. If the hole comes at the depletion edge somehow, it will be immediately swept away this side, because for hole this is lower energy, it goes like that, for electron it comes like that, right. So, immediately it will be swept away. That immediate sweeping away of the minority carrier is what contributes to J naught, okay, minus J naught current. That is what is contributing to minus J naught current. You see, any minority carrier that comes at this edge, electron, will be swept away this side, which means the carrier current flow is this side. Similarly, any hole that minority comes at the edge will be swept away to the other side, which means the hole current is also to this side. So, both these electrons and holes current are to the negative side, that is why it is minus J naught, which means the reverse saturation current is in the direction opposite to the forward current. When you apply forward bias, if you remember, electrons are injected from this side to that side, holes are injected from this side to that side, the net current is in the positive x direction, if you remember, in a forward bias. In reverse bias, the current is very small and that current is in this reverse direction, okay, J naught is minus J naught, okay. So, why will the minority carrier come at this edge? The minority carrier might come at this edge because of random diffusion. Within this, minority might diffuse and they might randomly come here, no. So, that will get diffused. Similarly, minority electron here, minority hole in this card randomly diffusing and they might come here. So, they will be swept away on the side, but there is no majority injection. Holes cannot be injected from here to there because there is a huge barrier. Electrons cannot be injected from this side to that side because there is a huge barrier. So, electrons cannot be injected, holes cannot be injected, it is basically minority that is suddenly coming here and being pushed away, okay. Now, when I say suddenly, it has been basically diffusion, okay. So, here also you can solve the boundary condition in the sense that, you know, in the solution of the forward bias junction condition, in the solution of the forward bias, when we are discussing the forward bias condition here, there is a boundary condition that, you know, at large distance eventually your carrier concentration will become equal to the background carrier concentration, right, at large distances. So, that is one of the conditions. So, in this case, when you have a minority in a reverse bias junction, for example here, so what is the condition that will apply? So, essentially here I am drawing x, this is 0, this is Wn, this is minus Wp. The total carrier concentration at the depletion edge here has to be 0, but far away from the junction, okay, far away from the junction the carrier concentration, this is n side. So, the minority carrier hole concentration is given by P n naught, which is Ni square by Nd, okay. So, far away from the junction this is here, but close to the junction it will be 0. So, at the edge the carrier concentration has to be 0. So, it will go like this. You can actually solve the continuity equation with the appropriate boundary condition and get this, okay. Similarly, here it will be baseline will be Np naught, which is equal to Ni square by Na. At this depletion it will be 0, at this edge of the depletion it will be 0, and the derivative of this point and the derivative at this point will give you the respective current that might go, and this is the total concentration is 0 here, and that current if you add up will also end up as minus J naught only. That is the same thing, that is the same thing that you will get, okay. You can solve the appropriate continuity equation at the boundary condition that at this point it has to be 0, at this point it has to be 0, far away it has to be Pn naught, far away it has to be Np naught, then you will get the same value of the current. This depletion has become larger by the way. Okay. So, essentially the reverse saturation current is minus J naught, which is very low, and the forward current is just J naught e to the power minus QVA by KT minus 1. This is the total forward bias current, this is the reverse bias current. This flows in the positive x direction, this flows in the opposite direction, and this is a diode that behaves like a rectifier. So, this is a PN junction that can behave as a rectifier, and there are many things actually. If you look at this J naught, for example, J naught, this reverse saturation current, also the reverse saturation current manifests something like this, right. I told you this is J, this is your the voltage that you are applying. So, on the forward bias junction, of course, you will get like this. On the reverse bias side, it will get very low current like that. So, this is your minus J naught. So, very small current actually, almost very small. This J naught actually is Q dP by LP, Pn naught, which I can write as Ni square by Nd plus Dn by Ln, right, into Np naught, which I can write as Ni square by Na. So, it depends on doping, of course. If I increase the doping, then your reverse saturation current also will decrease. If I want a very low leakage, or when I block the block voltage on the using this diode on the reverse side, I try blocking the voltage. No, I am not allowing current to flow. So, if I want a low leakage very here, this quantity has to be low, so the doping can be slightly high. But more than that, it depends on Ni, and Ni square depends on e to the power minus band gap by KT. So, a small band gap leads to a very large Ni, intrinsic area concentration, if you remember, and a large band gap leads to a very small Ni, if you recall. So, essentially a larger band gap material like gallium nitride with a band gap of 3.4 eV will have very small Ni, and hence your reverse current will be very small, should be very small, right. Whereas for a smaller band gap material, say if I take a smaller material like germanium, 0.7 eV. So, Ni is large, Ni is very large. If Ni is large, then your J naught also is large, which means this reverse current is large. So, a wider band gap material will have a better rectifying property than a narrower band gap material, because a narrower band gap material will have a larger leakage current or larger reverse saturation current. So, please keep that in mind, and this is a very important point actually to design PN junction diodes. For example, this reverse leakage current that you are getting, with which you are essentially blocking the voltage, is very important in power devices, power electronics. As a photodetector, this is called the dark current. Without shining light, this is the current you are getting. So, this leads to noise. So, if you can lower this, your noise, your noise will become less and your performance will improve. So, you can want to use a wider band gap material for many applications like that. Okay. So, we will wind up the class here. So, we have finished up the PN junction in non-equilibrium. Under the application of forward and reverse bias, what happens? We have derived the expression for the current. So, this is in a sense the PN junction fundamentals that we had to learn to be able to understand many other devices. The forward bias and the reverse bias current expressions we have derived, the physics of that we have explained, okay, the diffusion component and all. The next class, the beginning, we will also dwell upon a little bit more on the PN junction. We will think about the PN junction a little more, we will contemplate, we will ponder about it with reference to devices like LEDs or photodetectors or solar cells. We will discuss some basics of PN junction, okay, we will discuss some basics of PN junction and how there are some exceptional cases of PN junction like high injection effect and so on. So, those things also we will discuss a little bit, and after that we will move to before we go to metal contact with semiconductor, which is Schottky junction and so on, we shall cover one more very important aspect of PN junction, that is breakdown. How does breakdown happen in PN junction? And capacitance. A PN junction also has a capacitance on its own. So, that capacitance voltage or CV profiling, those things also need to be addressed. So, probably we will spend next 1-2 lectures on this entire things. Okay. So, today we will end the class here, we will meet you in the next class again. Thank you for your time.